For 200 years, one question has reshaped the railway over and over again. What is the best way to turn energy into motion? The answer changed from fire and water to oil to electricity drawn from the grid, and each time, the whole railway was remade. This is the story of how train power evolved. The journey runs in one direction. We start with a machine that carries its own fire and makes its own power, inefficiently, out in the open air. We end with a train that carries no fuel at all, drawing clean, centralized power from a wire overhead. Every step along the way was driven by the same four forces: efficiency, power, maintenance, and emissions. Keep those four in mind. They explain every change that follows. It begins with steam. In 1829, at the Rainhill trials, Stephenson's rocket proved that a steam locomotive could haul a train reliably and at speed. It was a triumph of its age, a self-contained engine that needed nothing but coal, water, and a clear track ahead. For the next century, steam would rule the world's railways. Here's how it works. Coal burns in a firebox, and the hot gases are pulled through dozens of tubes running the length of the boiler, heating the water around them into high-pressure steam. That steam is piped to the cylinders, where it shoves pistons back and forth, and those pistons, through connecting rods, turn the wheels directly. The spent steam blasts up the chimney, and that very blast draws the fire hotter. It's elegant, mechanical, and entirely self-contained. Engineers pushed this idea to its limit. The Union Pacific Big Boy, a 4884 articulated giant, was among the largest steam locomotives ever built, made to drag enormous freight trains over mountain grades. It was magnificent, but it was also the high-water mark of a technology that was running out of room to improve. Because for all its power, steam was deeply inefficient. Only about 5 to 10% of the fuel's energy ever reached the rail. The rest went up the chimney as heat and smoke. Worse, every locomotive needed constant water and coal, frequent heavy maintenance, and a crew to feed the fire. Measure it against our four drivers, and steam fails almost all of them. Poor efficiency, brutal maintenance, filthy emissions. The railway needed a better engine. After the Second World War, that better engine arrived, the diesel. Burning fuel inside its own cylinders, a diesel engine was far more efficient than steam, needed no water stops, ran for longer between overhauls, and could be started at the turn of a key. The promise was obvious. The problem was getting that power to the wheels. A diesel engine has a stubborn flaw. It makes no torque at all when it isn't turning, and it only works well within a narrow band of high speeds. A train, meanwhile, needs maximum pulling force from a dead stop. You could connect the engine through a clutch and gearbox, like a car, but the clutch would simply burn out under a heavy train. So pure diesel mechanical drive only ever worked for small, low-power machines, the yard shunters. One clever fix was hydrodynamic drive, perfected by Voith. Instead of metal gears, it uses fluid. The engine spins an impeller that flings oil at a turbine connected to the wheels, and with a ring of fixed guide vanes between them, that fluid coupling can multiply torque smoothly, from a standstill upward, with no clutch to wear out. Diesel hydraulic locomotives were light and capable, but the fluid wasted energy as heat, and the transmissions were fussy to maintain. The real breakthrough was to stop using mechanics altogether and use electricity. The diesel-electric locomotive doesn't connect its engine to its wheels at all. Instead, it turns the engine into a generator and the wheels into electric motors. This became the standard across most of the world's non-electrified railways, and it still is today. The chain is simple. The diesel engine spins a generator, making electricity. That power is rectified into direct current and fed to traction motors mounted right on the axles, turning the wheels. There's no gearbox and no clutch. The electric motors deliver full torque from the very first instant, then smoothly up to full speed. The locomotive is really a mobile power plant on rails. End to end, it converts roughly 30 to 35% of its fuel into motion, several times better than steam. So why did diesel-electric win? Run it past the four drivers. Efficiency, 3 times steam's. Power, full torque from a standstill, with locomotives easily coupled together for more maintenance. No fire to tend, no water to take on, far longer between overhauls. And emissions, while still real, were cleaner than a coal fire. For railways spread across long, lightly used routes, it was the perfect machine. But there was a more radical idea still. What if a train carried no engine and no fuel at all, and simply drew its power from the grid? That's straight electric traction. Take away the heavy diesel and its fuel, and you're left with a lighter, quieter, more powerful machine, supplied by power stations that are far more efficient than anything you could fit on board. The power comes down through an overhead line called the catenary. A carrier wire, the messenger, holds a level contact wire below it using small hangers called droppers, and balance weights keep the whole thing taut. A sprung arm on the roof, the pantograph, slides along the contact wire to collect the current. The wire is even strung in a gentle zigzag, the stagger, so it wears the pantograph evenly instead of cutting a groove. Some lines run direct current at hundreds or a few thousand volts. Main lines often use 25,000 volts of alternating current, which needs less current and lighter equipment. Electric traction sweeps the foredrivers. Efficiency. Around 90% of the energy reaches the rail, and during braking the motors run backwards as generators, feeding power back into the wire. Regenerative braking. Power. The highest pull for its weight of any train. Maintenance. No onboard engine to service. And emissions. Zero at the train itself. The catch is the cost of stringing the wires, which is exactly why it pays off most on busy lines. The final step changed not the power source, but where the power lives. Instead of one heavy locomotive pulling dead carriages, why not spread the motors along the whole train? In 1964, Japan's Shinkansen did exactly that, a high-speed electric multiple unit, or EMU, with powered axles all down its length. It set the template for high-speed rail worldwide. Spreading the motors brings three quiet advantages. With many driven wheels gripping the rail, the train has far better adhesion, so it accelerates harder and climbs steeper grades. With no bulky locomotive, the weight is spread thin, lighter per seat, and gentler on the track because track damage rises steeply with the weight on each axle. And freeing up that locomotive space means more room for passengers. Distributed power is simply more efficient end to end. Put the numbers side by side, and the whole story snaps into focus. Steam turned only about 7% of its fuel into useful work. Diesel-electric reached around a third. And electric traction delivers about 90% at the rail, though, fairly, the power station upstream has losses of its own. 2 centuries of engineering, and the efficiency climbed more than tenfold. Trace the arc 1829, rocket and the age of steam. The mid-20th century, the rise of the diesel. The spread of electrification under the wires. In 1964 onward, the distributed high-speed EMU. At every stage the engine moved further from the train, from fire in the firebox, to a generator on board, to a power station miles away. And every one of those steps was pushed by the same 4 forces. Efficiency, from a wasteful 5% toward 90. Power, from slipping driving wheels to torque from a standstill on every axle. Maintenance, from daily fire tending toward a sealed electric motor. And emissions, from a coal fire's black smoke to zero at the train. Efficiency, power, maintenance, emissions, the 4 drivers behind 200 years of change. So we're next. The wires keep spreading, and the lines they can't yet reach are turning to batteries and hydrogen, quiet, clean ways to retire the last diesels. The direction is set, cleaner energy, delivered ever more efficiently, all the way to the rail. From fire and water to power from the grid, the train has been chasing one goal for 2 centuries, to turn energy into motion as cleanly and efficiently as possible. And it's still chasing it. Thanks for watching Learn Railways.